Happy day and welcome to everyone. Today's lesson is actually on speeding you up on VSEPR. So my hope is that I could give you any set of, it's got 4 bonds with lone pair of electrons, and you could say, ooh, that's a seesaw and a regular tetrahedron. Or I can say it's got 3 bonds with 2 lone pairs of electrons. You're like, ooh, that's T-shaped. So I want you to kind of get a little bit faster at figuring out what these shapes are. And the best way to do that is through repetition, okay? So there are a lot of studies about this, but trust me, if you typically repeat things 3 times, it usually ends up being sent into your memory, okay? So what we're going to do is we're going to use the simulation. I'm going to ask you some questions, and then you answer the questions correctly, okay? So please make sure that you're paying attention here. Try not to write anything down. Just try to make sure that you're paying attention, okay? So first situation we have is you have 2 atoms. 2 atoms, no matter what, is linear. It's 180 degrees. Now, this could be polar or nonpolar. Depends on what these 2 elements are. So if they have a difference in electronegativities, then we could say it's polar. One of them is pulling more, so pulling polar. One of them is pulling more on the electrons. That would be polar, or it could even be ionic, and it pulls so hard that it removes the electron, a metal, for example, in that situation, and so then that would have a positive, negative electrostatic attraction. Now, let's go through and let me actually get rid of the single bond, and let's make this obey the octet rule. The only way that you're going to obey the octet rule with 3 atoms, so 2 atoms no matter what is linear, 3 atoms, we actually have 2 choices of shapes with 3 atoms, okay? So if it's this way, where we've got 8 valence electrons going around the central atom, and it's obeying the octet rule, we would assume that we're only looking at the central atom as far as the extra electrons are concerned. So this would have 8 valence electrons, it's 180 degrees, and so you would see something, for example, like carbon dioxide would do something like this, and so that's linear, okay? Pretty easy one. Now, what can happen is, one of these instead could be a single bond, okay? And if it's a single bond, then this is not obeying the octet rule. I would need a lone pair of electrons. And now they're saying that it's actually a 120 degree bond angle. Now, it's easy to remember because it kind of looks like that bottom section of a triangle where you would say that the whole thing equals 360. And so if I did have a line going straight up, which one of the shapes is trigonal planar, right? Then that would be 120 degrees times 3 equals 360. Okay, so this shape is called bet, so we've got 120 degrees. And remember that if we actually had real atoms in here, then that could be an even smaller angle, bond angle, depending on how attracted these are to each other, okay? All right, now what happens, we can get another lone pair of electrons. So let me switch one of these into another single bond. Well, this is 2, 4, 6, but I could add another lone pair of electrons, still bent, okay? So this is still bent. The only difference is, instead of being 120 degrees, since these lone pairs of electrons take up more space, it's now 109.5, okay? So it's either linear or bent. Let's just start right there. Let's see how you do, okay? So let me remove all. Let's just do 2 double bonds, and let's remove the name here, and let's remove the bond angle. What is the name of the shape, and what's the bond angle? All right, hopefully you answered that this would actually be linear and 180 degrees, okay? All right, let's go to the next one here. All right, let's remove one of these. And now I'm going to add a lone pair of electrons, okay? So my question is, what's the name of the shape, and what is the bond angle? Ready? Okay, and you should have said bent, and this one is actually, remember, in this case, it's still separated quite a bit, 120 degrees, 120 degrees, okay? Let's try the next one. So let's take off our double bond. Let's make it a single bond here. And then let's add 2 lone pairs of electrons, okay? And what is the shape here, and what is the bond angle? Remember, these are going to take up more space here. Okay, and hopefully you answered that this would still be bent, but now it's 109.5. And remember, it's not set in stone. And actually, let's take a look at a real molecule here. Something like SO2, for example. This does accommodate, sulfur can accommodate more electrons. Now, if you were to go to draw SO2 out, you would have drawn it this way. You would see that you could actually obey the octet rule. If I put my S in the middle and then my 2 oxygens around, and I go, now I've got 6 valence electrons for each one of these, so it would be a total of 18 valence electrons. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16. Where do my last 2 go? Well, they would have to go on the central atom. So I'd put my last 2 on the central atom, The only thing is, I still am not obeying the octet rule, so okay, fine. I get rid of those two and I put a double bond in. And this is a very valid resonance structure for SO2. But the other thing that does actually happen, because sulfur can accommodate more valence electrons, is in addition to this, and I can also switch the double bond over for another resonance structure, is I could also have two double bonds with that lone pair of electrons. Now, the oxygens are obeying the octet rule, so around each oxygen I have 2, 4, 6, 8, 2, 4, 6, 8, but around the sulfur I have 10. Now, why is this one valid? The reason why this one's valid, and I actually wouldn't expect you to write this one down, I would only expect you to write this one down, but because it goes into the d orbitals, that's why sulfur can actually accommodate more valence electrons. But really, in this situation here, if I check my formal charge, I get 1, 2, 3, 4, 5, 6, and sulfur formally actually has 6 valence electrons, so that actually works. Each oxygen has 1, 2, 3, 4, 5, 6, and 6 minus 6 also gives me 0, going all the way around it, whereas this does have a positive 1 and a negative 1 formal charge, okay? And so whether you switch it either way, so this is a valid Lewis dot diagram, but because there's that lone pair of electrons up there, it does still create that bent shape. Take a look at the bond angle. I would normally have said that it would be 120, but this is 119. So again, some gray areas in working these out, okay? And same thing for something like the water molecule. The water molecule, instead of giving us a 109.5, we would have expected a 109.5. This one says 104.5, okay? So again, just wanted to make sure that I let you know that there is some gray area that is in there. All right, let's move on now. So that's it for 3 atoms. Let's move on to 4 atoms, okay? So that means I've got a central atom and one in the middle. Now, this doesn't look like it obeys the octet rule, but remember, Betty and Al. So boron is fine this way. Now, aluminum, again, would normally be ionic, so I typically just like to call this boron. And so you want to check the electronegativity differences for any of the metalloids, but if it does create a polar, or in this case it would be polar bonds, but then what's the molecule type? Well, it's going to be nonpolar because everything is separated equally, and this does work, and this is called trigonoplanar. And just like we said before, it would be 120-degree bond angles going all the way around it, and no matter how you spin it, it's going to be 120 degrees, okay? All right, so now let's see what happens if, and by the way, you could have one of those as a double bond, same exact thing, still obeying the octet rule, and it still is nonpolar because the double bond does shift, so this is still trigonoplanar, okay? So now instead, let's add a lone pair of electrons. What's going to happen? Well, we know it's going to bend it, but they don't call it bent now. Instead, we call this trigonal pyramidal. Okay, so this is trigonal pyramidal, and you can see again that our bond angles look like 109.5 on here. Okay. All right, and we also know that we can add one more lone pair of electrons. Well, what happens when we add one more lone pair of electrons? Uh-oh, now it goes back to being a T-shape here, okay? So we've got 90-degree angles in the T-shape, and you could actually have one more lone pair, and it's still T-shape as well. Uncommon, but it does happen. So if we've got one lone pair of electrons, it's the pyramid shape at the 109.5-degree bond angles. If we add another lone pair of electrons, then it goes to the T-shape, and the T-shape is, it's 90 degrees between here and then 180 between those two, obviously, okay, but the 90-degree angles between there. And that's it for 4 atoms, okay? Let's go back and let's recap what we've done so far, all right? So we've got linear, and then let's take this off. Let's make it, so that was it for 2 atoms. For 3 atoms, this is also linear, and so we know that this is going to be 180 degrees. Now again, what happens if instead I add a lone pair of electrons to it? Well, if I add a lone pair of electrons to it, what did you guess? It is bent. And again, this would be 120 degrees. If I add a second lone pair of electrons, it's still, but again, I need to get rid of one of these. And so now it's 109.5 is the typical bond angle that they'll use in this situation. Okay, let's get rid of these. Now, here we go. If I add a 3rd atom into there, so one more bond in here, what is the name of this shape and what is the bond angle? All right, hopefully you answered trigonal planar or planar equilateral triangle and 120 degrees. All right. So now what about this shape? Let's add a lone pair of electrons. If I add a lone pair of electrons, the name of this shape is, hopefully you said trigonal pyramidal, and now we've got 109.5 degree bond angles. All right, let's do the next one. I'm going to add another lone pair of electrons. What happens when I add a second lone pair or a third lone pair of electrons? What happens to the shape, and what would our bond angle be? All right, take a guess. Did you say T-shaped and 90 degree and then 180 but 90 degree bond angles? Hopefully you got that part right. All right, let's move on. So now we are going to try out what happens when we've got a fifth atom, okay? 1 in the middle and 4 going around. Well, this is tetrahedral, okay? So yes, when you draw it, you make it look like a plus sign, but it's really not. The bond angles are not 90 degree bond angles. These are actually 109.5. Okay, so this 109.5 keeps coming up. So now we've got 109.5 between all of them. Typically, this is going to be a nonpolar molecule unless one of these atoms are different. All right, so we add a lone pair of electrons to it. What happens? This is the seesaw shape. Okay, so again, we call it seesaw or a regular tetrahedron. So imagine having kids sitting on the opposite sides of the seesaw. One goes down, one comes up. So kind of like that little seesaw thing there. Okay. All right, what happens when I add a second lone pair of electrons? Well, this is weird. It does not come up on top. Oh, and by the way, this is 90 degrees between the two that are closer to each other and 120 degrees. So where it creates like that seesaw shape, that's going to be 120. So this is 90 between the two, the parts that are like kind of the seesaw part that's sitting on the ground. And then between the other two is 120 degrees. Okay. All right. Well, when I add a lone pair of electrons, it creates a square. My atoms actually form a square. We call it square planar, and the two lone pairs of electrons end up on either side there, okay? And that's it for having 5 atoms, 1 in the middle and 4 around, okay? So recap on this part again. So let's see how we did. Let's remove all, and let's get our 4 bonds here. Oh, okay, and let's remove this and remove our bond angles. Okay, here we go. Ready? If we've got 4, what is the name of this shape and what is the bond angle? All right, hopefully you said tetrahedral and 109.5, not 90 degrees, 109.5. All right, next question. What if I add a lone pair of electrons to it? Okay, what's the shape? What's the bond angle? Go for it. All right, hopefully you said a regular tetrahedral or seesaw. And now our bond angle is going to be 120 degrees and 90 degrees. Okay, so 120 going along the bigger end. All right, what if I add another lone pair of electrons? All right, I'm going to add another lone pair of electrons. All right, here we go. Okay, hopefully you said square planar, and that the bond angles would actually just be 90 degrees. So I didn't go over that. They're just 90 degrees going all the way around, okay? All right. So now we're moving on. Hopefully you did well on that part. Now we're going to move on, and we're going to take a look at the next one, which is having 6 atoms. Before we do this, let's go right back to the beginning and see how we do, okay? So I'm going to go right back to the beginning where let's remove all, and let's get linear. Okay, now I'm going to add a second, and remember originally it would look like this, so this is still linear, okay? Now, I did want to come back to this because you can have, if you have 2 single bonds, you actually can have 1, 2, 3 lone pairs of electrons, and when we do that, it comes back to being linear. So if you have 2 lone pairs, it's bent. If you have 1 lone pair, it's bent. But if you have 3 lone pairs, it can actually go back to linear. So I did want to come back to this shape as well. And this typically is nonpolar. As long as these atoms are the same at the opposite ends, then that would be considered not a nonpolar molecule as well. Okay. All right. So let's get rid of these and let's get our shapes down. Okay. So again, this is linear with 180 degree difference. If I add a lone pair of electrons, what happens? Bent. Very good. If I add a second lone pair of electrons, so let's come back here. So instead of 1, I'm going to add 2. Did you say bent? Very good. If you said bent, and again, now it's 109.5. All right. Now, again, if I have a third pair, we said that could be linear. Okay, let's get rid of these. All right, now I'm going to add another bond. So if you have 3 bonded with no lone pairs of electrons, what is the name of the shape? Trigonoplanar. It is trigonoplanar. Now let's add a lone pair of electrons to it. Add a lone pair of electrons. Think about it, think about it, think about it. Did you say trigonopyramidal? That is correct. Now let's add another lone pair of electrons. What are we going to get? Think about it. So 3 bonded and 2 unpaired. Did you say T-shaped? You're right if you said T-shaped. And again, you could have a third one on there. It still stays as T-shaped. Okay, 90 degrees and then 180 around the big one, but 90 degrees here. Okay, let's do the one that we just did. So let's get rid of our lone pairs of electrons. What if you have 4 bonded? 4 bonded? What are you thinking? Did you say tetrahedral and 109.5? Let's add a lone pair. Think about it for a second. So I want to know again the bond angle as well as the name of the shape. Add it. Did you say seesaw? And also, again, on this one, we've got the 120 at the bigger part, and then we've got the 90 degree at the smaller, on the smaller side. Okay, let's add a second pair of electrons. Where is it going to go? Think about it for a second. Did you say square planar? It's going to create a square, and it's in a plane, and then we have our 2 lone pairs of electrons. What's our bond angle? 90 degree bond angles. Okay, now we've got 90 degree bond angles, the perfect square. All right, now let's go to having 6 atoms. Okay, we're almost done. We're almost there. Okay, so 6 atoms. Let's get rid of our lone pairs, and here we go. We're going to add one more, and we know that this is called the trigonal bipyramidal. Easy way to remember it, I call it tri-bi. So I've got tri like trigonal and then bipyramidal. Bi is 2 and tri is 3. Now, there is a 120 degree angle. So some of these are 90s. You can see that some of these are 90s. But in the back here, I don't know if you can see this. Oh, there we go. We've got 120 degrees between some of these here. So there's a bigger bond angle between the 2. So it's like the 3 is going to create the 90s, but those 2, between those 2 is actually 120 degrees. So we've got 90 and 120. Again, that's trigonal bipyramidal. Okay, let's add a lone pair of electrons. What happens? Well, we get a square, but, so it is the perfect square with 90 degree angles between them, but we also get this pyramid shape. So it's a square pyramid, okay? These are all 90 degree angles, okay? All right, so that's it for having 6. So now let's go to 7 atoms. 6 bonds, 7 atoms. Let's get rid of the lone pair. And if you guessed it, by adding one more, we call it octahedral. And you can see that we've got these 90 degree bond angles going all the way around on this octahedral shape. And that's it. That's all of it. Let's see how you do if we go back and we recap. Let's start with the 4s. Okay, I feel like it'll be good starting with the 4s. All right. So, with 4 atoms going around, what is the shape? What is the bond angle? All right, hopefully you said tetrahedral and 109.5. Let's go to the next one. We're going to add a lone pair of electrons to it. What happens when we add a lone pair of electrons? Think about it for a second. So, what's the shape and what's the bond angle? All right, hopefully you said a regular tetrahedron. Again, that's going to be 90 and 120. And let's do the next one. I'm going to add another lone pair of electrons. All right, here we go. What's the name of the shape and the bond angle? Okay, hopefully you said square planar again. And these are all 90 degrees. All right, now that's it. That's it for having the 4 atoms around that central atom. Okay, now let's go to what if we have 5 atoms around the central atom? Okay, so 6 atoms in total. All right, what do we think? So if I just add one more bond, what are we going to get if we've got 5 going around the central atom and the bond angles? All right, hopefully you said trigonal bipyramidal, and this is 90 and 120. There's that 120 degree angle, and the rest of them are going to be 90 degree angles, all right? Okay, let's add a lone pair of electrons. Think about it for a second. Name and bond angles. All right, I added it, and here we go. It's that square, but it's a square pyramid. So since it has one underneath it, that's a square pyramid, and these are all 90 degree bond angles. All right, and the last one, let's take off this lone pair of electrons. Let's add one more. So now we've got 6 atoms going around the central. What is the name and what's the bond angle? All right, and hopefully you said octahedral, and these are also all going to be 90-degree bond angles. You guys are awesome. I hope this worked out for you. Please make sure and rewatch this anytime, retake the quiz, so that you know that you've really got these down quickly. Happy day, everyone.